Now a few words about the classic Probit and the classic Tobit models. So as I already mentioned, for the Probit model, well, we'll take the function in the index expression as a cumulative standard normal distribution. So the f of x sub I beta that we used in the previous expressions is now the same as the phi xi beta, which is the cumulative distribution in the standard normal. As a result, just using the same expressions as before, the probability of observing an event y sub I equal 1 is the cumulative normal standard normal density of the explanatory variables times the coefficients, and similarly the conditional expectation on average. What is the probability of getting a 1, of seeing the event, given the values of the explanatory variables, is the cumulative standard normal density evaluated for that value of the explanatory variables. And as we've already seen, the effect of a change in the explanatory variables on this conditional expectation is really what we're interested in. So again, in contrast to the linear regression model, where that effect is the estimated coefficient, the estimated coefficient as such is not really that interesting in a Probit model. What we're really interested in is this marginal effect, and we already know that it's going to be nonlinear. It's going to change with different values of the explanatory variables. For the Probit model, this happens to be the partial derivative of the cumulative distribution function, which is in fact the density function by definition. So we use the same notation here as before, with phi in orange designating the standard normal density function. And so the marginal effect in a Probit model is the density function evaluated at x sub I beta times the specific coefficient that corresponds to the variable that we're changing. So it's a nonlinear function of the explanatory variables. It's not constant, and it depends on obviously the coefficient of the variable, the full range of values that the explanatory variable takes, and then where it is in the particular distribute density function, where it is the shape of that density function makes a difference as well on how fast or how slow it changes. So then we go back to our linear regression in a latent variable model, and the Probit model is a normal latent variable model where we now specify the random error u sub I as following a standard normal distribution. So everything is the same as before. We saw it in general. X sub I star is y sub I star is x sub I beta plus the error term u sub I. The error term is standard normal because we need to set the variance equal to 1 for identification purposes. We saw this scaling issue. We can multiply everything by a constant and it's still, everything remains the same. So it's not really the value of the latent variable that matters, but it's its sign. Okay, then as before, we switch from the latent variable to an actual observable with the same probability condition. To observe a 1, we have the latent variable y star sub I to be positive. Remember, the sign matters, not the value. We write that in our linear regression, linear specification condition as x sub I beta plus u sub I needing to be positive, or that's the same as the cumulative distribution of u sub I evaluated at x sub I beta, which in this case is the standard cumulative standard normal. So the probability of observing an event is the cumulative standard normal value evaluated for the x sub I beta. Estimation of the Probit model is typically done by maximum likelihood, but that's not the only way to do it. I just present it here just to give you a frame of reference before we move to estimation of the spatial model. So in this classic Probit model, we assume independence, so then the events are basically independent binomial random variables, and they're binomial because they happen or they don't happen with a probability p sub I, which is the probability of our latent variable being positive, which is the same as a cumulative standard normal distribution. So everywhere where we will have p sub I, that will be replaced by phi xi beta for each I. So since the observations are independent, the likelihood consists of the product of all the probabilities for the events that actually happen, with y sub I equal 1, and the complement 1 minus p sub I for when the event does not happen. That is standard binomial. In the likelihood function, we replace the p's by the phi's. So it's the product of the individual for all the observed y sub i's. It's the product of the phi xi beta. For the all the y sub i's equals 0, it's the product of the complement. And after a little bit of algebra, we see that this is the product of the phi xi beta to the power y, sum of yi, that should be, and then the sum of 1 minus I. There's a slight typo in here. But then when we take the log, we get the sum of the yi's times the log of phi and 1 minus yi and the log of the complement. This is still a little bit awkward, but since for the standard normal distribution is a symmetric distribution, so we can play some tricks here. The complement is the same as the cumulative probability of the negative of xi beta. So then when we define a new scalar, 2 times y sub I minus 1, this will be 1 if we observe y sub I, and will be minus 1 if y sub I is 0. Then we can write this very concisely as the sum of the logs of the standard cumulative normal distribution evaluated at q sub I, x sub I, beta. So the q of I basically manages the sign of xi, x sub I beta. It's positive for y sub I equal 1, and it's negative for y sub I equals 0. So that's just standard notation. Then I just give this as background. We don't really want to dwell on this. The first order conditions, as we've seen before, for maximum likelihood estimation, they're the so-called score. The first partial derivative with respect to the parameter set to 0 is this complicated expression, but what really it boils down to is a sort of an orthogonality condition. We saw similar conditions when we discussed the generalized method of moments, and in fact, one can estimate a Probit model by a GMM type procedure. And if you look very carefully at the expression for the estimation equations, the score with respect to a particular parameter, say beta sub k, is a weight, and we'll talk about that in a second, times what looks like a residual. Y sub I is the observed value, minus phi xi beta, which is the predicted value, the probability of observing y sub I equal 1, times xk. And this is, as I said, some kind of similar to an orthogonality condition, where you have that the product of the residual and the explanatory variables has to be zero. We saw that in our discussion of GMM estimation in the linear regression model. The estimating equations there were also of this form. There was the residual and then the x. Now this wi, w sub I, comes from the score, this complicated expression that includes both the density of the standard normal as well as the cumulative distribution of the standard normal. And in fact, the ratio of the density evaluated at x sub I beta over the product of the probability and its complement, the phi times 1 minus phi, that is this weight. And this will come back a number of times later on. It plays an important role in defining a concept of a generalized residual. Because the notion of a residual is not really that obvious. We have the true error term, the u sub I, which we model in the linear expression, but that is related to the latent variable. So the true error term, in fact, would be y sub I star minus x sub I beta, but we don't know what y sub I star is unless we simulate it, of course, which we'll get into in the estimation. So we can take a naive residual, which is 1 or 0 minus the probability that we get from the cumulative standard normal, so y sub I minus phi x sub I beta, or we can use this concept of a generalized residual, which is a weighted or scaled version of the naive residual. So we have the same expression, y sub I minus phi, but it's scaled by the density divided by the cumulative probability times its complement. And we'll see this expression under a number of guises later on as well. This is a notion of a generalized residual, which we need because the true error term is not operational, and then the residual cannot really be related to a y sub I star. Okay, now to close, a few words about classic Tobit. The Tobit model is a case of censoring where we only observe the dependent variable partially, but we observe everything for the explanatory variables. And a classic example is the purchases of durable goods, like an automobile purchase. We can survey a number of people and we ask them, did you buy a car? If they say, no, we don't have anything on the latent unobserved variable of propensity to buy a car, but when they do buy a car, we know how much they spend on the car. So that's a little richer, if you wish, than the binary 0-1 case, and it's actually quite a common case. You can think of it in terms of a marked point pattern. So a simple point pattern is just 1 for a point, 0 for no point. A marked point pattern would have an actual value associated with the point. So, for example, in ecology, you would have, is there a tree or not? And if there is a tree, you have the length of the tree or the size of the crown of the tree or something else, right? If you say you look at the location of grocery stores, there is a store, yes, 1, there is not store is 0, or if there is a store, you can say a lot of things about the store, square footage, how many employees, all kinds of things that you could model. So the Tobit model then, again, is a linear form of this. We start again with the latent variable expression y star sub I linearly related to xi sub I beta and the error term. Now, slightly different from the binary case, if the latent variable crosses the threshold set at 0, then we actually observe a dependent variable and we observe the latent variable. So y sub I is the same as y star sub I and is a linear expression. And then when the latent variable does not cross the threshold, then we don't see anything. So this then, and I won't spend too much time on it, this is actually fairly technical, fairly complex. Then the actual model for the observed y is complicated. One way to deal with this is just to ignore this complication and just do the regression for the values that you observe. But in fact, that ignores the fact that you are not explaining the instances where there is no observation. So if you want a richer model, then you have both the zeros in the model and the non-zeros in the model. That's really what it boils down to. So then the non-zeros no longer have their usual symmetric normal distribution, but they're truncated. They start at 0. It's only for the positive values. And so this creates a very complex hybrid where basically for the unobserved latent variables, we just know the probability that they're unobserved, which is the probability that the latent variable is less than 0 or equal to 0. And then for the observed y sub I, we have this complex expression on the slide, which only remotely resembles a linear regression, but it is because of the truncated nature of the normal distribution. So sigma is the standard error of the error term u sub I. It's not 1 in contrast to the Probit. We have the cumulative phi normal distribution, standard normal, and then we have the density of the standard normal. So this is a very complex animal, and as a result, the log likelihood is also very complex. It's a mixture of a discrete distribution for the unobserved ones, and you see the 1 minus p there as the first term. That's basically what that is for the zeros. And then for the ones, we actually have the y sub I observed, and then it's a form of a regression model. And so the notation, these expressions become very complex. We won't dwell on this. One thing to keep in mind for the Tobit model is that it is very sensitive to misspecification. And this is important in practice because the assumption of normality is a tenuous one in many social science applications where we deal with highly skewed distributions. So right there, we're in trouble. Heteroscedasticity causes problems as well. And of course, spatial autocorrelation does as well. So for the Tobit model, we're actually very interested in specification tests to make sure that this framework that we work in actually holds. Because if it doesn't hold, then the maximum likelihood estimates obtained by using the likelihood function that we just saw will not be consistent and will have all kinds of problems. So this is kind of a quick review of the background of Probit, classic Probit and classic Tobit before we move on to the spatial models, which we'll do next.